Alright, welcome to another AQA A-level chemistry video. Today I'm going to be making a video on amino acids. I'm going to go over the basics of amino acids quickly, and I'm going to be going over new content that you would have not probably known, and then about amino acids under different conditions. And yeah, that's it really. So let's get straight into it. So there are approximately 20 naturally occurring amino acids in the animal cell. So an amino acid has the general formula RCH NH2COOH. So RC and there's a H there, and then there'll be NH2COOH. I like personally writing it down. Like, I don't like that diagram here, but I think this is a better way of doing it like this here. R C H COOH, and then you have your amine group here. RCH NH2 COOH. Alright, cool. So then amino acids contain an acid group, which is the carboxylic acid, and a basic group, which is the amine in the same molecule. The NH2 group is on the carbon. The NH2 is on the carbon that's next to the carboxyl group, and so they are known as alpha amino acids. So when the amine is bonded to the carbon that's next to the carboxyl group, because sometimes you have the R here, and then or sometimes there's certain examples where you don't have this amine here isn't bonded to the carbon that's next to the carboxyl group, but you have to worry about that. Generally in AQA level chemistry, you're just going to get the alpha amino acid group. I haven't seen an example where you have to show your understanding of a beta or amino acid group. But just this is enough. This is all you need to know about. I mean, obviously the R groups and more, but in terms of the general structure of amino acids, that is what you need to know. And so obviously amino acids have two functional groups. They have both a carboxyl group and they have a amine group. So we call these compounds, as I said before with other compounds, this is when you have two functional groups on the same molecule, we call that a bifunctional group. So yeah, let's get straight into it now. Let's go into the next part. So acid and base behavior, right? So the carboxyl group is acidic and can react to bases by donating a proton. So this is the part. So this part you should know now. This is what you should know about. This is the basics of amino acids. But the second part is that the acids and base behavior. So the carboxyl group is acidic and can react to bases by donating a proton. This is the part. This is the part that you may have heard of it before. I mean, you should know about amine being able to be basic, or it can act as a base in a way. Because it can accept a proton, which is a Bronsted-Lowry base, and this acts as a Bronsted-Lowry acid because it donates a proton. But I'm just going to cover this. Is probably a part of it that you probably haven't done before, but you need to understand that because of that, we have to mention that, and especially in your exam, there will be examples where you have to show your understanding of that. So the carboxyl group is acidic, so it's an acid obviously. So carboxyl group is acidic and can react with bases by donating a proton. So it can react with bases by acting as an acid by donating a H plus, or breaking off this OH bond here and releasing a proton or a H plus. The amine group is basic and can react with acids by accepting a proton. So you can actually accept a proton here, form an NH3 plus. I'll show you an example later on. So you can accept a proton there, H plus. And amino acids are amphoteric. So because amino acids are both, because this can happen on the same molecule, both an acidic and basic behavior on the same molecule, we call the molecules like this amphoteric. So amino acids are amphoteric because they contain both acidic and basic groups in the same molecule. Side chain. So amino acid contains an R group, which is a side chain. This is different for different acids. So alanine has an R group of CH3. So actually, I probably should have put this. You know, that's it. That's fine as it is there. I'll leave that there. Yeah, I'll leave that there. So, we've talked about the amino acids general formula of it. There's two side groups, so the two functional groups here, and the NH2, the amine group, the carboxyl group. It has hydrogen, but I'm not going to talk too much about hydrogen. I mean, that's pretty just standard. Everyone knows about that. But the R group, the side chain, so an amino acid contains an R group, which is a side chain, and this is different for different amino acids. So, for example, alanine has an R group of CH3. Methionine has, I'm not going to go through the full length of methionine. Everyone knows glycine, because glycine's R group is just another H group. Cysteine and methionine are the only two amino acids that have sulfur and can do disulfur bridges. And so on and so on. You don't need to know all of the amino acids. You don't have to know that for A level. Don't worry about that. But just know there are certain examples of compounds that, if they have, you need to know about the bonding in R groups, which you should know from GCSE. But I will be going through that in the next video, which should be about proteins. So if I haven't gone through that, it'll probably most likely be in our next video. But here I'm just going to go through the very basics of amino acids so you can kind of go through that. So amino acids, right? Talk about the amino acid structure. That's terrible. Alright, so you have an NH2 group, obviously. I keep saying obviously for some reason, but that's probably something I need to probably stop saying. Now, NH2 group is obviously I keep saying obviously, but it's basic. And you have your R group, which is, it can be both. Your R group could be basic, acidic. It really depends. It's unique. That's the point of R groups. It's unique. For different amino acids, so different amino acids have different R groups, and I mean this is again the reason why I'm telling you about amino acids, the basic things about amino acids. When you learn about things like chromatography and different types of chromatography, column chromatography, understanding things like the R group can be both basic and acidic. It can have different affinities to the well, there's different types of stationary phases in when you actually get to learn about chromatography and the different types of chromatography, different types of stationary phases. I'm not going to go too much onto that one, but understanding the basics that, for example, different R groups have unique properties for each amino acid, and that allows you to be able to determine which amino acids that you have. So R groups are quite useful. Knowing that different R groups have a unique property in terms of its basicness or acidicness, and that will determine how strongly attracted it is. It makes it easier for us to determine which type of amino acid that we have, and that is how we determine amino acids mostly. So unique for different amino acids. And you obviously have your H group, but nothing really special happening there. It won't usually break off, so it's just the H group. And then you obviously have your, why do I keep saying obviously? But you have your carboxyl group, and that is obviously acidic. Great, so probably condense this, make it a bit more shorter. Leave as is now. Anyway, the zeta ion forms. Now, this part you definitely wouldn't have learned about or have any clue about, so I'm going to go through this one and try and make it as clear as I can for everyone. But the zeta ion form. So an amino acid could exist in the zeta ion form. And what that zeta ion form is where you have. Now, I probably should have shown it in a different example. I'll show you like this, because maybe skeletal formula can be a bit confusing for some people seeing it like that. I like seeing things in the structure formula as they are, because it makes it a lot easier for me to kind of get grips with it before I do. I mean, I can understand that, but maybe drawing it like this makes it a bit easier. NH3 plus. Great. So I probably want this bit. So the Zwitter ion form. So molecules of all ions having separate positively and negatively charged groups are known as Zwitter ions. So an internal acid-base reaction in an amino acid causes the nitrogen on the amine group to accept a proton from the carboxylic acid group. So if a basic reaction is happening, where in this case, if the only basic reaction that could happen apart from the R group, whichever one it is, if it's with the amine group, then it will accept a proton and it'll become NH3 plus. But if it's an internal acid-base reaction, so it's both an acid and a basic reaction, then so for example, a positive charge is on the protonated nitrogen because it accepts a proton. But if it's a basic, if it's a positive charge is on the protonated nitrogen because it's got a basic reaction where it's gained a H plus, whereas a base if it's a high pH or a basic reaction is happening. No, is it high pH? Yeah, if it's in high pH and the acid part here is reacting with base, then it will lose a proton. It will lose a proton. So and the negative charge is on a deprotonating oxygen because it's lost a proton to the acidic conditions. So the ionic nature of amino acids gives the higher melting points than expected. So once it's in this Zwitter ion form, right? Once it's in this Zwitter ion form, because it's now an ion, it actually has ionic bonding, which actually gives it stronger ionic bonds, and therefore, if there's strong ionic bonds, it'll have a higher melting point because it forms a giant ionic lattice. If this part here didn't make sense when I talk about the positive charge on protonated nitrogen and a negative charge and why that happens, I'll go through it again. So I'll go through it specifically here. So if pH on a Zwitter ion, right? At low pH, the carboxylic acid will not be protonated, so it will have no charge. And so basically, at low pH, right, the carboxylic acid isn't going to lose a proton because there's only H plus. There's a high concentration of H plus in the solution, so it isn't going to lose H plus. Isn't going to lose a proton. So nothing will happen to this carboxyl group. So it will actually look like this. Why did I do that? Yeah. What I meant to do was. Actually, no. I'll just draw it down here for you. I forgot. I was gonna draw it down here. Right. So we know. So let's just go through this part here. I know I haven't read out the full sentence yet, but we know for certain that this part here, nothing will happen to this. So it will remain as this. Nothing's gonna happen to that part because it's at low pH. There's already a high concentration of H plus in solution, so it's not gonna lose a proton. The R group, I mean, also R groups can differ because it will have, depending on what's on your R group, so that could change. But for the sake of it, I'll just leave that as R, just for the sake of that. The hydrogen group, nothing's gonna happen to the hydrogen group. However, because this is now a low pH, it's very acidic now, and the amine group, which is basic, will have accepted a proton. Because it's basic, it's going to accept a proton. That's the properties of a bond-state Lowry base. So the nitrogen will have accepted a proton, and now it's become NH3 plus. Now, I'll probably just draw like this. So it would have been initially just been like that, but now that it's gained a proton because it's now in acidic conditions, it's like that. And you have to draw the extra hydrogen, or you can just do it like this. You can also just do this NH3, but the most important part here is that you show the positive charge. It's 3 hydrogens and a positive charge, and that here would signify that you have now you're showing your understanding of that in acidic conditions this will get protonated. That's what you're showing to the examiner. It's showing that you understand the properties of the amine and the carboxyl group in the amino acid and how it reacts in different conditions. And at high pH, in the exam, right, they're never gonna just say what's this in acidic conditions. They'll insinuate. They'll say draw what its compound would be if you had an excess amount of nitric acid in your in a beaker with the amino acid in it, and they would say draw what the compound would look like, and you know the nitric acid is, but it's a very strong acid, and therefore it's a very strong acid, this can get protonated. Hopefully I talked about that enough. Hopefully you get what I'm trying to say. But now if I was to flip that, if it was at high pH now, the amine group will not be protonated, so nothing will happen to the amine group because it's not going to gain a proton because there's no proton for it to gain, right? So there's not enough protons for it to gain, so nothing will happen to that, to have no charge. And the carboxylic, but however the carboxylic acid will be deprotonated because now there's a lot of base around the acid, so that's a part of the carboxyl group. So I say that's a part of the amino acid, which is the carboxyl group. So now it will become deprotonated and it will lose a proton, or donate a proton, which is how Bronsted-Lowry acids work. So we know that nothing's going to happen. Oh, that's not like that. There, nothing will happen to this amine group here, and it's important to show that. They're also looking about what hasn't changed. So they expect they expect that should be correct. But if you've done something to this, they'll say, well, you lose a mark because you've shown something else here that's not meant to happen. So showing that you understand that nothing happens here and something happens here for that case. But in this case here, nothing happens to the amine. The R group, as we said, is very unique. So it depends on what the R group is. If it contains, they'll try and make it obvious for you by having an amine or a carboxyl group. But it could be an amine. It could be anything really, but they'll try to make it as obvious as possible to show you whether or not it's being, whether or not it will react with the acid or a base. And if this group had an amine on it, you need to also show the, for example, if it was let's say I haven't got the exact name of the R group, right? But let's say the R group was this. CH3 here, but then H here, and then an amine here. Sorry for the noise. If there's an amine here, even though it's not, even though it's on the R group here, it's the entire compound is in base in this reaction here, right? So now you have to also show, you have to represent this as well, like this. If that was the R group here, you'd also have to show on here. And it's the same principle if it was for the base or the acid, wherever the R group is, if it has an obvious signing of where it should be a positive charge or that there's a gaining a proton, make it obvious there. Right, I'm going to stop talking about that. I think everyone gets what I'm trying to say here. I don't want to keep rambling on. But in this example here, there's it's basic, generally very basic. So they'll have deprotonation. And it's lost the proton here. And that's how you represent it. You can represent it like this. They do allow it. I like drawing it like that though. But they do allow writing it like that though, instead of writing it like the structure formula. And unless they specifically say they want it in a structure formula. Then yeah. So at an intermediate pH or as a solid salt at room temperature, which depends on the amino acid, the main secret present is this bitter ion. So the one thing they might say, instead of it just being in an intermediate or basic, if it's an intermediate pH, or yes, the one thing they might say is just an intermediate pH, but one thing they also might say is that what if it's at it's not in solution, if it's a salt or a solid at room temperature, then it will be a Zwitter ion as you've seen up here. So as a salt or as a solid or in intermediate pH, it's this, a Zwitter ion. So both it would be the amphoteric behavior of both acting as both being both protonated and deprotonated. So this intermediate pH is known. So when it's like this, when it's in this Zwitter ion form, we call that intermediate pH the isoelectric point. So the point where it's acting as a Zwitter ion in the intermediate pH, we call that the isoelectric point. So yeah, I think I made this very clear here. But it's like this because it's lost the proton here, and it's gained this proton. So it actually loses the hydrogen from. So in acidic conditions, right, it loses the hydrogen here, and it can be gained by this by the amine here. Of course, it could have, if it's from an outside compound, then it could also react as well. But hopefully, I made this as clear as possible, and that is the end of the video. I'll stop rambling now.